When it comes to magnets, there seem to be some interesting opinions on how we should add them to our 3D prints. It turns out there's no wrong answers. Well, actually, one wrong answer. So I suppose we should get to it. This video is sponsored by Elegoo and the new Centauri Carbon 2. I will be using the CC2 for the practical aspects of this video. If you want to learn more about the Centauri Carbon 2, then it just so happens I've already reviewed it, which I'll link below in addition to links to the product. If you also have a CC1 and you're interested in the canvas kit that's just been released, you may or may not know about that. I've also made a video about that, and you can find that in the link in the description as well. Let's get into it. For some reason, the first option that always seems to surface is stopping the print midway, inserting the magnets and continuing. It's an interesting idea because it's a manufacturing method that you can't easily replicate with traditional manufacturing. But I think that's about where this ends. It's kind of novelty. Firstly, this idea was thought up back in the day when nozzles looked like this, meaning the shape, and this is actually a Centauri Carbon nozzle, a third-party Centauri Carbon nozzle, but the official ones look like this. By the way, that is one of the things I like about the Centauri Carbon and the Centauri Carbon 2. Both of them take the same nozzle. Also, it's nozzle-shaped, meaning it looks a bit like a traditional 3D printer nozzle. You can replace the whole unit in here if you want, but you don't have to, because it's just a nozzle and you can unscrew it just like you could on, say, an Ender 3, if you have been around long enough to have ever used one of those. That does feel strange to say. But yes, they sell both configurations, so I mean, I think all manufacturers should do this. Why is it so hard? Anyway, my point was that the official Elegoo nozzle is magnetic. And this is becoming increasingly common because nozzles are getting made out of steel and not brass. And yes, some steels are magnetic and some are not. The only way to really find out is to put a magnet against them. And the reason why being magnetic is a problem is, well, if you use your imagination for a second, what do you think happens when you put magnets in 3D prints and then put the nozzle back over the top of them? Exactly. Nonetheless, you can do this if your nozzle is not magnetic. There is no reason why not, but there are downsides. The main one needs me to get out the special paper. And we are going to be seeing a lot of this paper. Actually, no, that's not true. We're going to be seeing very little of this paper because this paper is rubbish. You probably recognise it. It shows magnetic fields. I think I've seen this on a lot of science channels. And you might think it's cool, but actually, no, it turns out this is rubbish. This paper, though, this is cool. I don't think we're going to get through this video if I spend ages showing you this paper, but also I don't think we're going to get through this video without me showing you this paper, so I'll do it in a minute. But hopefully I could show you that distance is the enemy of magnetic field strength. So the point is that embedding magnets is not peak magnet. It's not getting the best out of your magnet. You're losing some strength, which may or may not bother you. We'll get onto that. Peak magnet, though, is option number 2, which is friction fit. This is as simple as making the holes just the right size to push the magnets in, using what we call an interference fit. This is almost certainly the simplest option once you know how big your interference fit holes need to be. How do you figure that out? Well, trial and error. If you don't like that answer, then good news. I made this quick tool that you can use to generate a test part and save it as an STL, and you can use this to figure out your best friction fit size. It saves a lot of time and effort. So yeah, that really does solve the trial and error problem. The benefits of friction fit are ease of use, ease of design, all you've got to do is put a hole in something, and no extra parts needed. The downsides can be quite serious depending on your application, but it's possible, if not likely, that magnets might in the future come out of a part with friction fit magnets, and this is the right time to mention that these magnets are a very bad idea around people and animals that might swallow them. A couple of notes when it comes to friction fit. One of them is ribs. This gives you a crush area for insertion. It's probably material specific how well these work in practice. I had mixed results with them. I found them a little bit annoying, to be honest, but you can add them. Some people use a hexagon. I found that one even more annoying, but some people like it. I personally prefer ribs, so I added those to the calibration tool. And remember, when you're using these, you need to change the tolerances. The hole needs to be bigger. The advantage to using things like ribs is that it also means that if you want to, you can use the next option in conjunction with a friction fit, and that next option is glue. I want to mention magnet size first though. It's entirely up to you what size magnets you use, but I found the best ones overall are these ones. They're 6mm by 3mm and they're freely available and cheap, and I'll link some in the description as well. Neodymium magnets are quite brittle, so the 3mm depth makes them significantly more robust, and of course the deeper they are, the more friction you get against the sides of your interference fit, or there's more surface area for glue if you're doing that. Nothing huge to say about glue. For most plastics, superglue works fine. You might have a preference, but superglue is okay. You need somewhere for the glue to go, so you will need to leave some space behind, around, or behind and around the magnet. Otherwise, you're just squeezing the glue out when you put the magnet in. You could optionally design in some features under the magnet so that the glue can get extra grip, but I think just enough space will usually do because FDM is not generally that neat anyway on top surfaces. So I think glue will generally work quite well, especially if you combine it with a friction fit. And some space behind it. I had an idea to use a retaining clip. I think it's interesting and seems to work. I'm not sure if I could be bothered with this though. The basic idea is that you're kind of putting a clip in on top of the magnet to stop it from popping out. It seems okay in theory. But related to that, I also had the idea of adding a lip slightly higher than the part, and you could either melt that or push it down in a vise or hammer it down. The downside with this method is that once again you are adding a arguably unnecessary gap over the magnet. Again, you've got more distance than you need to have, so the magnetic field is weaker. While we're talking about using heat though, you might be tempted, and I've seen a lot of people suggest it. They suggest using a soldering iron to heat insert magnets, just like you would with heat inserts. It seems like a really good idea. Trust me, it absolutely isn't. I'm going to test a magnet using my phone's magnetometer, and then I'm going to put it on this soldering hot plate for literally 10 seconds. The soldering hot plate is actually cooler than a soldering iron typically would be, and while that's happening, let's have a look at this magnet paper. The green stuff is nickel flakes in an oily liquid. They are magnetic enough to follow the magnetic fields. The new paper, though, is actually liquid crystal. You might have seen the thermometers you can get for fish tanks that are similar to this, but we don't have enough magnification to see this, but in this case, the crystals get tilted by magnetic fields. The stronger the magnetic field, the more towards blue the image gets. You might think that this paper, therefore, would be able to measure the strength of a magnetic field of a magnet, but unfortunately it's just not that simple in real life. What we see on the paper, in fact, are the magnetic fields that aren't doing any useful work. The ones that we call completing a circuit, there's a thing called completing a magnetic circuit, and you won't see that at all on the paper. And that's an interesting thing we need to cover too. When you're placing multiple magnets, if you place them all the same way in your part, with the poles facing the same direction, what you do is you create a large plane that behaves roughly like a large magnet, but not a good magnet. And the reason you might want to alternate them instead is because two things happen. We can see the extreme of this on a naked print bed. You probably don't give much thought to the humble print bed magnetic sticker, but these are quite clever. What these stripes represent isn't quite alternating fields. To explain it, I need to show you a thing called a Halbach array. These have magnets arranged in a very specific pattern that causes constructive interference in the magnetic flux lines in a manner that makes one side of the pattern nearly twice as strong, and the other side, the back, almost zero. Now, it goes without saying that life can't be that simple, so capitalism has found a version of a Halbach array that isn't strictly a Halbach array, but it simply alternates the north and south fields, and that's actually what it likely is on this print bed and these magnetic stickers here. It's almost as efficient, or it's efficient enough, and presumably it's cheaper to manufacture. Doing this has the same benefits, including less leakage, so there's less chance of affecting nearby objects. But also, another benefit is what we call registration, which is the ability to use magnets to align things, which is something you don't get with a single magnetic field. There's just a tendency to allow two parts to slide around on each other. Now back to the toasted magnet. We've been talking for ages, but remember this is only 10 seconds of heat that this magnet has been subjected to. This is representative of probably about what you'd do if you tried to heat insert a magnet, even if you tried to do it quickly. Or as it actually turns out in real life, heat insert a piece of metal that's not a magnet anymore. Turns out, the temperature at which magnets become unmagnets is not that high, especially for neodymium magnets, which is basically all the magnets I have here. This is why higher temperature magnets are usually the ones used on print beds. You can get them, but they're not common. This is, by the way, effectively an irreversible change. The magnet is now completely useless, and it's remarkable how little time this actually takes. So, I think it's case closed for heat insertion. Don't bother, don't do it. Pockets are next, and by that I mean side insertion. Again, the tool I made can do these for calibration testing. I found that they require different clearances compared to top insertion. The advantage to these is also the downside, which is you're concealing the magnets, so they are less likely to be pulled out by magnetic forces, and if you alternate them, they should hold each other in two, and you have more possibility to put a plug in and seal them so that they don't come out and become dangerous. One interesting side use of the generator I made is that you can make a pocket test piece and ask for all the holes to be the same size, which should be the correct size, obviously. Merge this into a part in the slicer, and you've got an instant fridge magnet out of anything you want. I actually did get a bit carried away with this principle and also made this tool here. This is a bit more experimental, but it does actually seem to work. I've used it quite a lot. You can load any STL you want and just click where you want magnet holes to go. It doesn't really like flat surfaces because there's not enough triangles, so there is a button to increase the number of triangles to avoid massive holes in the sides of stuff if you try to put a hole in a big flat surface. Again, I'll link this in the description, and I suggest trying it out because who doesn't want to stick magnet holes in everything? So we still need to talk about venting. The test tool has an option for putting vent holes in. You see, when you push a magnet into a hole, what you're doing is you're displacing air. And if you have a really good interference fit, which is what you're aiming to do in friction fit situations, well, you're not displacing air. What you're doing is you're compressing the air, and so the magnet just wants to pop straight back out again. Sticking a vent in allows the air pressure to equalize, but also it's quite useful for reusing the magnets because there's absolutely no chance you're going to get a magnet out of a hole once you've put it in. Finally, just to go over some other methods that I haven't covered already, sticky back magnets exist. These work okay with some materials. If the material is greasy or the surface isn't prepared and smooth, they might not stick. They also don't really look that professional in my opinion. They do have their place, they're not that strong either. And you also have these, which are fairly common. These are basically the same magnets, but they've got holes in for screws. If you need to know how to put screws into prints, made a video about that. I think, in my opinion, if I was to choose, the best general method of inserting magnets, and the one that I would use more commonly, is friction fit for prototypes with the option of glue for permanent use. And you can design for one and use the other, really, can't you, if you put a vent hole in the back. And if you aren't using magnets for pure strength or registration, then you can also side insert them. Inserting magnets mid-print is generally a hassle that we don't have to bother with if we don't want to, unless you are very intent on them being completely encapsulated, and you just like doing it, that's fine. But that does come at the cost of strength, and of course you will have to ensure that they don't get too hot in the process. Let me know if you have any methods that I haven't thought of or tried, and we'll talk about them in the comments. I will see you next time. Thank you for watching.